Thanks everybody for coming in today. It's exciting to have a chance to share this with you. I can see people, some friends, some family, some people from the department. So that's all really exciting and thanks for joining. So the talk today is going to be about how geometry and physics can help us develop methods for discovering robot behaviors, even when they're pretty complicated mechanisms. So let's get started. In the past decade, we've seen some impressive advancements in the capabilities of robotic platforms. The robotic snake can climb stairs as well as navigate tightly constrained spaces. Some manipulators, like the one in the top right, can handle deformable objects like clothing. Chimp, in the bottom left, can enter disaster scenarios and do complex tasks such as valve turning. Cassie, in the bottom right, is an articulated legged platform that can navigate uneven terrain. Mechanical complexity is necessary for these systems to accomplish sophisticated tasks, but adding each joint exponentially increases the space of shapes a robot can exhibit, presenting challenges for modeling, planning, and control. So this curse of dimensionality inhibits our ability to engineer useful behaviors, persist through injuries and malfunctions, and adapt to new environments. So how are some, relatively successful companies approaching this problem? So Boston Dynamics approaches this resource-intensive process with time, people, and money. So they have a big engineering team, and they go through the careful characterization and modeling process for their robots. And they have the money to quickly fix their robot when it breaks. So Atlas and Spot are great platforms, but it's a resource-intensive process to get the robot that you want. Google took a different approach. They tried to attempt this problem with lots of data and a high-fidelity physics engine. Now, if you look at what this robot's doing, this humanoid, it learns this really interesting policy, but it's doing something weird with its left hand. We're not sure if this is some, nuance of the reinforcement learning algorithm that they used, or there's some infidelity in the simulation that they're using, but it's not something that we would do when we're developing, our own systems typically. So it seems like either might not be the total answer. Drilling down more on the modeling component of the problem, you usually see an effort accuracy trade-off. So if you want to work with simple models, that might be lower effort, but you'll probably have a less accurate model. So in the walking community, people like to use mass spring models to approximate how their system's bouncing along as it moves, along the ground. And that's a good rough, coarse idea of what the system is doing, but you can't really fill in those finer details that you might want for a more complex maneuver. As you go to the right along this kind of continuum, you can see a 5-link biped, so that's more complicated. And then you might even actually use the CAD models, build this full Lagrangian model of the system, like you can see with Cassie. Or like on the last slide, you have the option to build your own high-fidelity physics engine. Hopefully, you're building one that reflects reality pretty accurately. In this work, we're going to try to do something different, where we have a system identification or modeling algorithm that's low effort, but still maintains pretty high accuracy. In engineering, we typically don't get a free lunch, so we're going to have to use some structure in our problem to get there. So the motivating questions for this thesis are, when can insights from the geometry of systems make modeling, planning, and control problems easier? And then from any of these insights, can we bring them back into these behavior engineering and robot adaptation problems for actual field systems? So in chapter 1, we investigate the simplifications of being highly damped on robot modeling and optimization using the structure of mechanical connections. We will show the details of the approach and present its capabilities to rapidly engineer behaviors in a policy gradient optimization framework. We'll show that the method has promising sampling properties even on fairly complex experimental platforms. In chapter 2, we focus on the problem of expediently obtaining useful plans for navigation on arbitrary mechanisms. We again use geometry as our friend, constructing an optimization metric for primitive libraries that value the group-defined composition of behaviors. Rather than valuing the individual qualities of a behavior, we'll explicitly value the ability of behaviors for their contribution to covering the local space of maneuvers. In chapter 3, I'll speak to some extensions we made to chapter 1 so that we could begin to model soft robots and systems with momentum. And finally, I'll speak about some extensions and perspectives we gained from this work that might improve advanced mission-driven platforms. Okay, so getting into chapter 1, broadly speaking, geometric mechanics is a field dedicated to understanding insights that can arise from casting the configuration space of a system as a Lie group. People that have used Lie brackets in control theory might be familiar with some of the contributions of this field. Ostrowski showed in the 90s that Lagrangian systems are agreeable to these formulations when a system's environment is homogeneous. For example, the physics that govern the MIT cheetah, it doesn't matter where it is in the grassy field. So this robot could be closer to the building, closer to me, or the cameraman on the right side or the left side of the field. That doesn't really change the actual physics that govern the interaction between the robot and the ground. These environmental symmetries induce a topological reduction on the dynamics. The geometric insight, so to speak, is that the manifold describing the dynamics is more compact in representation and more amenable to analysis. Using this reduced Lagrangian, we arrive at 3 interacting physical variables. And these are pretty intuitive things. So in the blue, we have the body velocity. The green is a generalized momentum, and the R is an internal shape. And they correspond to these interacting but distinct equations in the middle. And we're actually going to look in this chapter at a more specific version of these types of systems. So unlike the cheetah, we're going to look at systems that have no momentum. So the P is going to equal 0, and therefore the P dot is also 0. And that's not going to be like this cheetah. It's going to be like a different class of systems that we'll get into in a bit, where the friction tends to dominate any type of momentum related interaction. Also, we're going to assume that we have high bandwidth control in the shape. And that's going to allow us to very precisely control different motions in the internal degrees of freedom of the system. So with these 2 assumptions, we end up with just the first part of the blue equation, which is this body velocity equals a shape-defined linear mapping of shape velocities. And this is a special model called a mechanical connection. This actual functional form should look really familiar to manipulation people, because it's the same type of interaction that takes joint velocities to pose velocities, where that A of R term is like the Jacobian of your manipulator. So this is a really simple functional form, and it's governing the locomotion of systems, not just where the pose of some manipulator is going to be. So in this work, we're going to see if we can exploit this model to help us find useful behaviors even on complex robots. An example of a system that would be amenable to this analysis is like the snake robot that you can see here. When the system is slithering around, the frictional contacts that act along its body dissipate the inertial features of the system, is what we tend to notice. So over the last 10 years or so, it's been shown by us and other robophysicists that a variety of animal and robot behaviors can be explained by this mechanical connection. The interesting part about this is these robots and animals have very different shapes, very different material properties, very different environments, but we can explain their motion models with the same functional form. So that's the interesting property that we're going to use moving forward. So previous work in developing optimal behaviors for mechanical connections there's some interesting work done by one of my committee members, Ross Hatton. And what he did was, when you look at these 2-dimensional systems, you can build a global model by taking the system and putting it at every single shape possible and sampling every shape velocity possible to build the global model of the system. And once you did this, Ross basically has developed some really nice analytical techniques for arriving at and finding optimal gates. What we were interested in doing this work was making the model was trying to take some of the insights of this process, which was there's really interesting models that we might be able to extract quickly from data, but we want to have a method that scales really well with dimensions when we don't have access to a global model. So in our approach, our improvement is going to be that we're going to develop a local understanding of a behavior and iteratively improve it via gradient descent. So rather than this approach on the left, the exhaustive empirical approach, we're going to build the connection in the vicinity of a behavior, or a rhythmic behavior is a gate, for example. And then we're going to use that local knowledge to keep adjusting the robot's behavior to find some performance that we think is really nice. And as you might imagine, as you build up into more complex systems, this is going to be a bigger win because we don't have to sample that whole shape space. So here's an example of a 3-dimensional shape space where we don't have to put the robot at all of these different points. So instead of spending hours or days on the system identification, we can spend minutes. Okay, so how do we actually build this local approximation? So for a physical system, R is our internal degrees of freedom, or our shape. And we're going to say that the behaviors the system is undergoing is periodic. So this theta can take some value 0 to 2 pi and map it to some shape on the robot. And then 2 pi comes back to 0. So just like trigonometry. And then our approximation is going to handle the immediate vicinity of the gate. This delta term is going to capture those perturbations, and they're going to be within some epsilon. So we're basically saying that in the shape space, there's going to be some tube of trajectories that we're going to model the behavior within. So the first thing that we wanted to do was test this modeling framework on simulated experimental data. And actually, I'll just take a minute to say I'm getting a little bit of feedback. So if your video or if your Zoom isn't muted, if you could do that, that would be helpful for me. Thank you. But yeah, so the first system that we worked with is this simulated Purcell swimmer. So this is a friction dominated system that can modulate those two angles, R1 and R2. And the way that we're going to run our simulations is to inject noise basically into a cyclic trajectory, and that's going to create this tube of different trajectories in the same neighborhood of each other. And the parameters for that you can see in the bottom right, and we're going to run each system for 30 cycles and then build our model from that data. So to give you some spatial intuition, here's a video. So when the system's oscillating, it creates these different points in the shape space. This data looks periodic in the time series. We have tools that allow us to understand this periodicity and understand what the average behavior is in terms of phase. That's what that red line is. And then we can take that average behavior and bring it back to the shape space here, right? So now this is a super useful way to organize our data, because we can zoom into a part of the cycle and we can look at this and say, whenever I change the shape of the behavior and the shape velocity, I can see in terms of my model how this is changing the body velocity of the system. So hopefully that was helpful in giving some spatial intuition, but on this next slide, I'll cover explicitly what's going on. So we take that model where the body velocity is a shape-defined linear mapping of shape velocities, and we partition it into perturbation coordinates. Our first order approximation is going to be, a Taylor approximation, where that 0th order term is going to be the average behavior that we're seeing per cycle. And then those first order terms are going to tell us, when you adjust the shape, how does the actual body velocity or body motion change? You can see the regressors of this calculation in the bottom left, and we estimate those in phase windows of the cycle that you can see in the highlighted red 1/8 of a cycle. So we'll build that model there, and we'll build it in each partition of the cycle, and then we'll wrap the coefficients that we compute together in a Fourier series to give us a notion of a model for the behavior. Great. So since we have these local models, the publication that I'm citing in the top right, we did some more work on actually validating that these models were accurate on the Purcell swimmer. Rather than looking at the accuracy right now, I want to take a look at the usefulness of the model. So is this model accurate and useful enough to actually inform behavior improvements in a robotic system? So we're going to use a policy gradient framework to do that. And the first two questions that we're going to ask to build this policy gradient framework are, what is a good way to parameterize the gates? And what is a safe and resourceful way to step through that space? Oh, and the thing that we're going to be optimizing in these simulated examples is the efficiency of the system. So how far it moves divided by the cost to get there. So the gate parameterization that we have it's called an ellipse with bump functions. And the elliptical fit allows us to fit a coarse representation of what's going on, which is that black circle. And then the added splines allow us to add some nuance at different phase regions of the cycle. So adding the elliptical fit with the splines allows us to, for example, approximate a diamond gate, which is in the red. So now we'll define how we want to step safely along the gradient. Given a candidate improvement gate, shown in red, we want to be able to ensure that it is supported by the history of shape space data that was collected during the experiment. If the new gate is too far from the average behavior, the dark blue line, the model won't have meaningful predictive quality in determining the outcome. What we want is a notion of a tube, shown in light blue, that wraps around the behavior and represents the history of observed experimental data. If a trajectory exits this tube, we don't want to use it. We use the Mahalanobis distance metric z of beta so that we can compute the likelihood that a trajectory came from the experimental data, assuming that the perturbations from the limit cycle are normally distributed at a given phase. The user can set z of beta by passing empirical cycles through the metric to obtain a reference value. So in the optimizer, we compute an efficiency gradient on the ellipse with bump functions parameterization. We slide along that gradient in the policy space, predicting the new efficiency with our data-driven model. We stop moving along the policy gradient once we've reached that limiting z of beta, which is 9.8 that you can see on the slide. So now we can take our locally optimal modification of behavior and run another set of experiments. So this is how we're going to do iterations with that policy gradient optimizer. Okay, so what does this look like in the simulation? This is like kind of the fun part. So we take a system that is not currently able to move with that gate, where it's just oscillating those two joints back and forth. We run that for 30 cycles, build a local model, and then slide along that policy gradient. We do that for 5 iterations, and we find a motion that's okay at moving forward, not super fast. 5 more iterations later, we can move about twice the speed. And by trial 20, we find a fairly efficient motion for locomoting. And what's interesting is there's a traveling wave that's going through the system, and it looks pretty serpenoidal, right? So this is something that's intuitive to us from looking at things like snakes. But what's interesting here is we didn't directly encode this in our parameterization with the ellipse with bump functions parameterization. The optimization found in a 169-dimensional parameter space that this was a successful strategy that could exploit the physics to move forward. Looking at the number of cycles that we actually used to optimize, it was 30 cycles per trial and 20 trials, so 600 cycles. If you were to use like a simplex gradient optimization technique, it would take you 169 cycles just to build that initial simplex. So this is pretty competitive in terms of how many cycles that we're using, and we thought that that was pretty interesting. So here we detail the results of the optimization across a variety of noise regimes, shown in the colors orange, red, blue, and green. Green, for example, had the largest amount of noise injected into the shape space and subsequently had larger tubes of data to build models from. For each color, 30 separate optimizations of 30 trials were run. The Purcell swimmers all start with 0 displacement and infinite cost of transport, which you can see on the low horizontal on the right plot. Each process, regardless of noise level, converges to a fairly close range of final cost of transport, indicated by the black line slopes in the plot of displacement versus cost per cycle. There's a distinct difference in the gates selected, however. Orange gates involve low amplitude motions in the joint space and result in low energy and low displacement. The green gates result in higher amplitude motions in the joint space and result in high displacement and high cost behaviors. It may be the case that the high noise in the optimization process incentivizes the swimmer to select higher amplitude motions that reject disturbances. Here, the mechanical complexity of the swimmer affords it the opportunity to select between such behaviors. So if we had like maybe only 3 joints in the system, it might be harder to have a low amplitude and a high amplitude behavior. And having these 8 joints is something that actually offers it that choice. So here, this is a different test. Rather than testing the persistence of the optimization across noise regimes, we test the lack of dependence of the gate optimization on the initial gate selected. In this analysis, we selected all paired combinations of joints and stimulate that pair with the same sinusoid as the initial gate. You can see each of these combinations highlighted in red in the top right, and there are 28 different selections. So each pair is run for 3 separate optimizations of 30 cycles. And what's really interesting here is that each converge to a close region in the performance space. The swimmers converge to this similar serpenoidal motion with a similar waveform. The only difference is that they're basically prioritizing the joints that you initialize the simulation with. So for example, the top left combination with those 2 on the 2 joints on the right, it would basically bias and have high amplitude motions in those joints in the final gate selected. but otherwise it ends up with a motion with a similar waveform. So we thought that that was pretty interesting, and overall it showed that the optimization did not depend super strongly on the initial gate chosen. So the simulations are really nice, but we want to do some sanity checks on hardware to make sure that this translates to the real world. So this was our first foray into doing that. We have this 5-link wheeled snake optimization with these wheels on the bottom of the system that make it easier to go along the link than against the link. We have 21 parameters per joint, just like the Purcell swimmer. It actually took 80 cycles to build the models for this system. That's more cycles than it took for the simulated data. We're gonna actually find out why that was in a couple slides, so hang on for that. And I think there's some interesting stuff to talk about here. So again, we're gonna optimize how far can this system move per cycle, and we'll put a quadratic penalty on turning. So before we get into the video, in the top right, I'm showing the exploration of the system through the shape space. And the bottom left, I'm plotting how far the system is going forward versus how much it's turning. And then in the bottom right, I'm just explicitly plotting the objective function as with the number of trials that the system is executing. So in this first trial, the system can't go anywhere, but it's building a model. Trial 2, it thinks that doing something with the back is useful, but it's not able to actually move forward. By trial 4, it starts displacing, but it's just basically changing orientation. By trial 6, it starts to leverage this wave that propagates through the back part of the system. Trial 8 moves, but turns a lot. And by trial 10, we actually find a pretty decent motion for translating. So that was interesting. The optimization took 27 minutes, but there's still that question of, why did it take 80 cycles to compute the model, right? So we decided to add double the joints to the system. That should, really break things if there's something weird going on here. But what we found was really interesting. So first thing, this system was so long and had such distributed mass that we couldn't actually control the shape on the high friction mat. So this mat that we used on this example to help the system move farther per cycle, the robot that I built on the next slide actually isn't even able to control its own shape because it's not strong enough to do that. So we took it off the mat and put it on the lab floor. Well, it turns out that the system has way smoother interaction with this like polished surface. And I didn't realize that the high friction mat was creating a lot of stiction or extra vibrations in my system, which was creating some observational challenges. So now, even though we have double the joints, we can build the model more quickly. So we were building models for this system with 30 cycles, just like the simulated data that we had previously. So in the first trial, the system doesn't go anywhere. It's turning a little bit. By trial 4, it's starting to propagate a wave through that back tail. In trial 7, it starts kind of jerking its head a little bit to start to translate. Trial 10, it's starting to translate pretty well. And by the time we get to trial 13, we arrive at a pretty good gate for translating. So this took 12 minutes of experimental data, pretty competitive for a system that has 8 degrees of freedom. So we were pretty happy with that result. So as contributions of chapter 1, we have a low effort, high accuracy system identification method for friction dominated robots. The strengths of this method are we don't need to specify the kinematics, the weight distribution, or the environmental properties of the system. And the models are built in tens of cycles, even on the 8 degree of freedom system. Limitations are we need that environmental homogeneity. I need to be, on the lab floor or a flat grassy field or a granular surface or a road or something like that. But the benefit is ideally when we go to the next new environment, we should be able to system identify quickly and adapt to it. The other limitations are the dynamics need to be friction dominated, and we need that high bandwidth control and shape. Great, so we just covered a framework for engineering behaviors on complex robots. However, when it comes to navigation, it's not always clear which behaviors are the most useful to engineer. When working with sufficiently complicated or unintuitive robots, world motions that seem useful to us may not be achievable or efficient for the robot to execute. Here we'll use the geometry of the workspace to inform an efficient and resourceful approach to generating behavior libraries. We'll find that this resourcefulness results in highly adaptive robots as well as very unconventional yet very functional robots. For traditional systems, we often tell the system how we want it to move. For systems like these, we want the robot to tell us how it wants to move. So these friction-dominated swimming platforms help us understand that unintuitive behaviors can be highly effective for planning. The left system can adjust the prismatic joints between the drag-absorbing discs. The system on the right can flap the 3 trilaterally symmetric joints. Neither of these systems has a non-intersecting gate that translates without rotating or rotates in place. Despite this, we designed 6 gate libraries for each system, exciting less obvious motions that turn and rotate. As we can see, the 5-step horizons of these robots demonstrate that they are quite effective at moving in the plane, just in ways that are less natural to us. Next, we introduce a metric we designed to incentivize robots to simultaneously optimize a collection of behaviors for their ability to cover a local space of motions. This will allow us to value a behavior for its contribution to overall mobility. This way, we avoid our tendency to overstipulate the qualities of an individual behavior. We call our metric coverage since it values the ability of a robot to reach a collection of local poses with a small collection of behaviors. Using geometry to our advantage, we consider any robot behavior as having a corresponding group motion, taking the robot from its body frame to a consistent displacement in the Lie group workspace after executing the behavior. By constraining behaviors to be gates with a shared starting point, we can link behaviors together. This allows us to coordinate behaviors in a convenient letters of words representation. What appears in this example as algebraic multiplication is a more complex sequence of right group actions that describe motion on the rigid body configuration spaces, SE2 and SE3. So for example, let's say we have a list M and the motions in there are A and B. So the 1-step motion horizon would be, well, pick motion A or pick motion B. At the 2-step horizon, you have AA, AB, BA, and BB. So 4 different places you can go. 3 steps, there's 8. So these, generate a variety of poses that your robot can make it to. So M will basically contain this set of motions up to 4th order motions. And by viewing the 4-step horizon, this is the smallest horizon that includes Lie bracket-like commutator motions, which are typically physically and spatially unintuitive. So finally, we're going to compute coverage by summing the weighted distances of goal points throughout the Lie group. And the way that we're going to do this is you can design it however you'd like. So while a densely filled volume might promote something like maneuverability, you can also distribute points along the XY plane to incentivize translation without minimal turning. Maybe if you had a surveillance robot where you wanted to visually track something while you're moving around the room, that might be a nice a circumstance where that would be nice to do. Great. So now we're going to compute coverage by summing these different distances of each goal point to the nearest available motion in M. And because these points are close, we can measure the distance by taking the norm of the displacement on the Lie algebra. This allows us to gain a notion of point distance even on complex configuration topologies like SE3. So we took the 3-link per stall swimmer and asked it to simultaneously optimize 3 behaviors to maximize coverage. We constrained the gate parameterization such that each behavior shared a base point. For each gate, we sampled the system for 30 cycles to build a data-driven model of the behavior using the methods of Chapter 1. The coverage points are equally weighted and uniformly distributed over a unit volume in SE2, which you can see there on the left. This unit volume contains translation of 1 body length and half of a rotation in either direction. Again, we are going to optimize the coverage over 4 steps, which you can see plotted on the left in just a second here. So this is the first motion that the swimmer has for all 3 gates. And then we're going to follow that gradient of coverage in the data-driven geometric optimizer. Then the swimmers figure out a way to move forward and backwards. After 5 more iterations, one of the gates starts turning as a way to start to fill out that space. Now 5 iterations later, finally recovering that space pretty well. And here are the correlating gates that generate that. So the way to read this graph on the left is I have 3 different gates I can choose from. If I run them for 1 cycle, I get the red horizon, but then I can choose to apply those 3 gates at the end point of the red locations, and that's where you get the green, and then the blue, and then the magenta. So here we go. Go to the next slide. There we go. So here we observe how the coverage optimization on the Purcell swimmer might change as more joints are added to the system. The plot here shows that the Purcell swimmers, regardless of the number of joints, are able to find high coverage gate libraries. Each optimization sequence starts with 3 zero displacement gates. Each of these 3 gates involves sinusoidal excitation of a single random joint. Each swimmer is able to find a collection of 3 gates that minimize the average distance to coverage points, evenly distributed over that unit volume in SE2 that we talked about on the previous slide. So no matter how many joints are used, we can see that the swimmers very quickly reach a point of diminishing returns. Some reach this point at about 10 trials. So for swimmers run at 2 cycles per second, this would require 7.5 minutes of experimental data. And that's not just to find a behavior, that's to find a functional plan for navigation. So comparable methods that can be applied to a general class of robots usually take on the order of hours to days to build, some type of optimized behavior library for navigation. So having something that can work super quickly can be really convenient when you want to do things like adaptation. So we build up this example to ask the question, how many joints does the Purcell swimmer need to be able to recover from an injury? The 3-link swimmers, after joint locking, are rendered unable to move. Their singular working joint is restricted to 0 displacement gates via the scallop theorem. The 4-link swimmers, shown in green, are able to improve upon the initial configuration. However, their final gate is not as strong as the uninjured 3-link swimmer. This suggests that the lock geometries of the 4-link swimmer may be challenging to compensate for with just 2 functional joints. The 5-link swimmer shows a strong improvement though. So adding more links than this does not result in performance that escapes the standard deviation of performance of the previous swimmer shown by the transparent color bands. So thus we'll make the argument that the 4 links, the 4 joints in the 5-link swimmer make it fairly good at recovering from injury. In the context of recovery from damage, complexity consistently makes learning easier and quicker. So here, mechanical complexity is actually seen as an asset rather than a liability for expediently recovering from damage. This is a fairly rare feature that results from using the system identification and optimization methods in this thesis. So next, I really want to hone in on why was there a different experience in the green band on the right and the red band on the right? So that green band, like we said, that's the 4-link swimmer, and the red is the 5-link swimmer. So let's look at 2 case examples to see what's going on there. So here's the 4-link swimmer. It optimizes its library that you can see in the top right. And the bottom left, we injure it, and it's not able to really recover very well. Whereas the 5-link swimmer, in the top right, you can see the initial optimization, then we injure it, and then it's able to recover quite well. It can fill out that space of at least planar motions fairly quickly. So really interesting example here where having that extra redundancy is really nice. If we wanted to use some insights from controls to maybe explain what happened here, when we go from 4 joints to 3 joints, technically, unless you're in a singular configuration, you still should be fully actuated on the 3-dimensional space of planar rotations. Whereas for that 4-link Purcell swimmer, going from 3 to 2 joints, now you are under actuated again. So that might be part of the reason, but still really interesting observation. Yeah, so now we really wanted to emphasize that we're not using the robot kinematics, we're not using CAD files, we're not doing any material modeling, okay? So we really wanted to emphasize this. So I went into the woods and literally just gathered sticks and bolted them onto the motors that I use for the snakes. So this is now a tree branch robot. So let's see what this thing can do. So the first thing that I did was I asked it to optimize moving straight. And I just had 2 joints in the backbone here. So it's able to move, but it turns a lot when it moves. And then when it tries to adjust for the turning, it finds this degenerate behavior that doesn't go anywhere. When I put 3 joints in the backbone, I was thinking maybe the redundancy would, fix some of the turning. issues, and it kind of does, but it still turns a lot when it's moving. That one's okay, but yeah, so it still turns a lot. So this is a perfect time to remind ourselves of some of the motivations for why we designed that coverage metric. We don't need to overstipulate that this robot has to be able to move straight along a line. We can let the tree branch robot tell us how it wants to move around the room. Great, so we're going to take this robot and optimize it for coverage. The first thing that I did here was I sampled 12 random gates, and I said, okay, take the best 3 that fill out your local coverage, and then we'll seed the data-driven geometric gate optimizer with that to make local improvements. So here's the seeded behaviors. We have something that translates a little bit, but is turning, and then we have 2 turning motions in opposite directions. As we iterate and go through some different cycles, you can see this next one, gate A, trial 5, that's pretty good at translating and turns a little bit. And then we have these 2 complementary motions that turn in place. Okay, so it might not be clear just by looking at those examples, but we can stitch them together by the representation, the letter of words representation that we showed previously, to show that we did improve the navigational capacity of the robot pretty quickly and pretty effectively. So this is the space of planar motions that in green that it was capable of exhibiting before the optimization, and the blue contains the motions that it was capable of exhibiting after the motions. So the contribution here of chapter 2 is that we generated this optimization metric termed coverage that was used to discover compact gate libraries whose composed motions span a region of local pose changes specified by the user. When combined with policy gradient methods of chapter 1, the strengths are unintuitive robots quickly learn functional policies for navigation. And you could say, include in that also recovering. So the mechanical complexity was observed as an asset for recovery. That's really interesting, right? That's really rare, and we don't see that often in robotics. Limitations, if you have a global model for your system, this is just kind of a reminder. If you can exploit that global model and build a really refined, optimized approach to locomotion, you should totally do that. We're working with systems where we really don't have access to these refined global models, so we want to be resourceful with that regard. And then one thing I wanted to include at the end is most people don't use just dead reckoning anymore for state estimation in the robot, but if you were, this would be a nightmare to use the coverage plans for that, because there tends to be a lot of turning with those plans, and due to the non-commutativity of motions on the planar workspace, it would be really hard to integrate your motions while turning so much. But most people, if you're using some type of external reference for localization, it really shouldn't be a problem. Great, so in chapter 3, we extended the system identification methods of chapter 1 in 2 important ways. So we're going to start looking at modeling soft robots and systems with momentum. So why extend the system identification algorithms to handle shape under actuated dissipative systems, which is our mathematical description of a class of robots that includes, soft and compliant systems. These types of platforms are providing new capabilities in manipulation, locomotion, and biocompatible actuation. So soft actuators can offer alternatives to rigid actuators that are obviously softer, but also cheaper and more damage resistant. This lack of easy to use, accurate system identification technologies in the field for soft systems is a main reason why we're not able to see them commonly used today. So here we will provide a system identification method that may work towards a solution for this broader problem. So for friction dominated or dissipative systems, we have 2 important equations on the left: the familiar body velocity equation and an equation for wrenches, tau, that they are a linear mapping of shape velocities. In the middle column, we split the shape and internal wrenches of the system into those that are controlled and those that are passive. Through basic algebra, we get an equation for the passive wrenches of the system in the top right. We'll make the assumption here that internal joints, let's see, there we go. So we'll make the assumption here that internal joints are constrained to the space of hooking springs and linear dampers, which are not that's not a particularly aggressive assumption, we think. That should at least capture the dominant modes of what you would expect in the passive systems. And even with this assumption, we think that this representation allows us to derive a convenient form for estimation of body velocities and the passive shape velocities that you can see in the bottom left. And by this equation in the bottom right, we can directly substitute in controllable torques for controllable shapes. And this is really important because for many soft robots, such as ones actuated pneumatically or with dielectric elastomers, for these types of robots, pressures, forces, and torques are typically, or voltages are more convenient to supply. So being able to rethink the way that we do our inputs is really important for this project. So here I'll talk about why the estimation structure we use is particularly convenient and practically useful for soft systems. So our estimation in the middle is a happy medium between the coarse, naive first-order Taylor approximation of the dynamics and the highly detailed, naive second-order Taylor approximation of the dynamics. We have enough detail to start understanding the nuance of soft systems and their physical interactions, but not so much that we'll probably overfit when we're just training on tens of cycles. And related to that, an important feature is that the size of a regression grows linearly in the number of passive degrees of freedom, rather than quadratically like you can see in that bottom row. For soft systems, which commonly are modeled as continuums, this is a critically important feature that can make the estimation tractable for high dimension representations of soft robot behaviors. So now we'll show the predictive quality of models using the regression structure motivated on the previous slide. We calculate the predictive quality of the model, gamma, by comparing the sum of absolute errors of the data-driven model with respect to the phase average model. The score is scaled from 0 to 1 and is calculated via the equation in the top right. RA contains the approximation values, RT contains the phase average values, and R is the ground truth. At gamma equals 0, the data-driven approximation has no predictive quality over just guessing the phase average behavior of the system, or like the average rhythmic behavior is what we're using as that 0 reference. At gamma equals 1, the approximation would basically be able to fully reconstruct the full ground truth behavior of the system. So we test the predictive quality on 2 example platforms. I designed this linear bladder swimmer, which can change the geometry of its bladder by modifying R2, which excites the passive component lagging behind it on the left. The change of drag induced by the bladder geometry and the oscillator and the oscillation of the passive block allow the swimmer to translate from left to right. So and then that's how that system moves. And for the Purcell's symmetrized cousin, the left and right pair of links move synchronously via the angular displacement from the horizontal. The left 2 links are passively attracted to this rest length via a torsional spring. On the rightmost column, we can see the magnitude of the periodic translational velocity and shape velocity. The ground truth is shown in black and the phase average behavior plotted in gray. On the adjacent graphs, we can see that the data-driven approximation error, shown in blue for body velocity and red for shape velocity, is much smaller than the phase averaged estimation error. The corresponding gamma readings above 90%, we can see the effectiveness of the approximation on these simple platforms. So we're getting almost 95 and above % for each of these. So very close to just building that data-driven model and understanding exactly how changes in the shape affect changes in the passive shape and body motion. So as has been a trend in this presentation, we want to see how this thing extends to higher dimensional systems. So we start with that 3-link Purcell swimmer, swap one of the joints out for a passive joint, and then the final test is actually taking 6 of those joints for the 9-link Purcell swimmer and turning them into passive joints. And we're still getting estimation quality of predicting over 80% for that tail joint. So we thought that that was really impressive and spoke to some of the strengths that we were hoping that we would see in the method. So like chapter 1, we have this low effort, high accuracy system identification method for friction dominated soft robots. The strengths are the same as chapter 1. We don't need to specify the kinematics, weight distribution, and environmental properties, and these models are built in tens of cycles, right? What's different is the type of systems we can apply it to. So in the limitation section, rather than having that friction dominated requirement, we can relax that into a friction dominated requirement on the position and shape dynamics. And we don't necessarily need that high bandwidth control and shape. We're letting some of these elements be passive. And I think it's important to note that one of the reasons we were able to build these models so quickly is that we made sure that the size of the regression grows linearly in the number of passive degrees of freedom. Great, so now that we've completed our analysis of shape under actuated dissipative systems, we'll take a look at system identification techniques in the perturbed Stokes regime. So in this section, we'll expand our capability to model systems that actually have momentum. My former lab mate, Matt Qualheim, is pictured here since he was the one that did the analysis to present a regression for systems in the perturbed Stokes regime. Matt applied nonlinear hyperbolic invariant manifold theory in a singular perturbation context to analyze a class of systems that decay in time epsilon. This epsilon is a generalized inertia damping ratio in the mechanical system. As this epsilon approaches zero, the dynamics collapse to that of Stokesian behavior. The Stokesian regression, shown in the first two lines, has regressors shown in blue. These are the same regressors that we observed in chapter 1, and as epsilon becomes greater than zero, we can see that the green regressors begin to play an important role in the dynamics, right? So that epsilon that you can see in the bottom row, as you increase that to like 1 or 10 or something like that, all of these terms are going to have way more impact on the evolution of that body velocity term. So my role on this project was to distinguish where and when this regression structure is practically useful for system identifying robots. To do this, I designed the paddle boat system shown above. The boat has a mast located at the center, but the paddles have no mass. These paddles can be scaled in articulation to act more like tails, which you can see on the right. Because the center of mass doesn't change as a function of shape, epsilon falls cleanly out of the dynamical model. So that was a special characterization of the system that we designed. So next, we will system identify the paddle boat over a range of epsilon to determine in what dynamical regimes these perturbed Stokes regressors give us, estimation quality improvements over those previously used Stokes regressors in chapter 1. So in these figures, gamma in part B carries the same information that it did for the under-actuated systems. It records the accuracy of an approximation with respect to the phase average model. This is scaled from 0, no improvement with respect to the phase average model, to 1, perfect reconstruction of the real behavior of the system. The bold shaded regions of B denote the perturbed Stokes regression accuracy, while the light shaded regions cover the Stokes regressor accuracy. Delta in part A shows the improvement of the gamma accuracy for the perturbed Stokes model over the gamma accuracy of the Stokes model. We can consistently see strong improvement in that range of the log of epsilon equals -1 to 1, or basically epsilon equals 0.1 to 10. So that range where you're starting to see those peaks in the graph. And this is consistent over a variety of gates, including flapping the paddles synchronously and flapping them in antiphase. Here we showed that these same trends extend to the extremal gates for the paddle boat and the Stokes regime. It is in this neighborhood that we expect the Stokesian regressors to perform poorly, which is in fact the case. Again, we see improvements for the perturbed Stokes model in the same general region of epsilon. So that's that log of epsilon equals -1 to 1 region. Here, I just did one example of a simulation where we can see that the true robot motion is in red, and we can see that the Stokes estimation causes some pretty substantial drift in the system, whereas the perturbed Stokes estimation is able to track the red fairly closely. So the improvement you could think of as if we were trying to predict where that paddle boat is going, if you didn't have the recent work in the green, you would be stuck thinking that your robot was where the blue one was. But with these new improvements, we would think that we're where the green robot is. Great, so this final graph, again, the theme, adding joints, seeing how things scale with dimensionality. We took that flapping gate and we tried it on the 4-joint paddle boat and the 6-joint paddle boat. And it turns out that the model accuracy improves with the number of dimensions in the system, which, is kind of surprising. And I think that there's some things going on here that are really interesting, where if we have really good regression structure for our dynamics, even having more complicated interactions, sometimes that we're able to actually capture those really well and still have high fidelity predictions for where our system's going to end up. So this contribution from chapter 3, part 2, is another low effort, high accuracy system identification method, but this time for systems with momentum. Same strengths as chapter 1, but the limitations change, right? So I'm keeping the limitations from chapter 1 so you can see them, but that friction dominated requirement, now we can have momentum play a small to medium role in the dynamics. Not a large role like that MIT cheetah, but the small to medium role that Matt has very carefully defined. Great, so getting back to the motivating questions for this thesis, I think I have a few minutes to wrap up. When can insights from the geometry of systems make modeling, planning, and control problems easier? And are there these generalized insights that we can bring back to field systems? So just a few thoughts here. Let's say I have a mobile manipulator and all of a sudden I run into a wall and warp that first link. Having a method that can recompute data-driven Jacobians in real situations could be really handy for regaining pose control in dynamic situations. Also, if you have some mobile system and a wheel kicks out, having a method that can actually let your robot figure out how to finish its local task and then upload it to, some fleet's information planning architecture could be really valuable. I think that snake systems are going to continue to advance and become more autonomous over the next few years. And I think that the tools that were developed here could be really helpful for that. So the really tough part about these systems is when they change in environments, it changes that whole continuum of contact along the body. So having algorithms that can embrace that change and quickly build a collection of behaviors that are useful in real world scenarios could be really helpful to take these systems from less teleoperated to more autonomous in the field. But speaking about teleoperation, I think that the perspective of data-driven oscillator models could be really valuable there too. So let's say that we have chimp turning a valve repeatedly, and we organize those motions, but then we label the successful turns and the unsuccessful turns. You could potentially find some physical understanding in the phase of the system as to why the unsuccessful trials are happening, and this could correlate to actual spatial rules that you govern in your teleoperation control, like don't bring all the fingers to contact the valve at the same time because you're going to have these indeterminacies of what contacts are actually governing the physics and things like that. So that could be really interesting. And finally, our robots are getting smaller and acting in more complicated environments. This is a bacteriobot that its goal is to transmit medicinal payloads throughout the body. If we have algorithms that are able to help these systems try new inputs and find useful behaviors, even in really complicated to model environments, we could have robots that do really important behaviors for society in general. So these were some future extensions and applications that I thought were just kind of interesting. But overall, in summary, we used information about the geometry and physics of a broad class of systems to build a portfolio of fast and sample-efficient behavior modeling algorithms. By building data-driven models of systems in their operating environments, we were able to compute high-quality policy gradients that produced useful behaviors reliably and quickly on physical systems. Using information about the geometry of robot workspaces, we were able to use the modeling and optimization techniques to discover resourceful strategies for locomotion. Yeah, so this was super fun, and I'm very thankful for the advising and support that I've received along the way. Thanks to my lab mates, especially Matt and George, who took me under their wing when I was just getting started. It was great to have a chance to share this work with you, and I'm very happy to take any questions. Thank you.